class, we are going to see the various computational models in embedded system. So first we must understand what is a computational model. So what is the meaning of computation? Computation is the process or the process of making, we can say. So when any embedded system is built, some model is used for designing the embedded system. So we call that as computational models in embedded system. There are many models. We will look into some of them in today's class. So like I told you, there are many models. So we have 6 types here. Let us look into it one by one. The first one is the data flow graph model, which we call it as the DFG model. So this data flow graph model is a data-driven model. So you know what is data-driven? Yes, we have studied what is event-driven. So what is event-driven? When there is an event, an action takes place. The best example is your airbag. When there is an accident, airbag opens. So that is event-driven. So now this data flow graph is data-driven. So when there is a data, the process happens or the process starts. Okay, so here what happens in this data flow graph, the data processing requirements are converted to graph. The data processing requirements are converted to graph. Okay, so your data flow graph is a data-driven model, and here the data processing requirements are converted to graph. So what are the various components that are present in a data flow graph? Okay, you need to understand. The first one is the process. Okay, the process is usually represented using a circle. You can also call this as a block. Okay, the second one is the data flow. The data flow is usually represented as arrows. Okay, so here the process is represented as circles. Okay, fine. And the process can be an addition, subtraction, multiplication, anything. Yes, and the data flow is represented as arrows. Okay, this is an inward arrow. So inward arrow means you call it as input. Okay, now you have an outward arrow. Okay, this outward arrow is called as the output. So two important components. One is the process, which is represented using a circle. Then arrows. If there is an inward arrow, it is called as the input. If there is an outward arrow from the circle, you call it as output. So where is this data flow graph used? I will tell you one domain. This data flow graph is used in DSP applications. So where in DSP applications, it is used in audio compression. It is used in speech recognition. So now let's take, you have a speech recognition system. So only if you talk, your door will open. Okay, so when you talk, your speech is recognized. So your speech is a data. Based on data, the system is driven. So it is a data-driven system. Okay, now let us take an example. So I have x is equal to a plus b, and I have y is equal to x minus c. So how do I represent this in data flow graph? Okay, so now this plus is a process, this subtraction is a process. So I put this plus here. This plus is a process. What is the input? The input is A and B. Okay, so input is represented using inward arrow. So this is A, this is B. What is the output? The output is X. So the output is represented using outward arrow. Now, the next one is y is equal to x minus c. So here your subtraction is an operation. So what is the output of this? The output is y. What is the input? The input is x and c. So the input is x, which is an inward arrow, and c, which is again an inward arrow. Okay, the output is y. Okay, so what is the value of x? We have already derived the value of x. So I connect this here. Okay, so inward arrows means input, outward arrow means output. So this is the example of your data flow graph. Okay, hope it is clear. Next, let us look into the types of data flow graph. Okay, there are two types of data flow graph. One is cyclic and the other one is acyclic. Okay, if you have feedback, you call it as cyclic. If you don't have feedback, then you call it as acyclic. Okay, and in your acyclic, you will not have multiple values for input variables. Similarly, you will not have multiple values for your output variables. Okay, so two types, one is cyclic, the other one is acyclic. Okay, now let us go into the next type. The next type is your control data flow graph. Okay, from the word itself, we understand this is nothing but it is control operations together with your DFG. Okay, so for your DFG, you have process, fine, which is represented using circles. Okay, now for your control, you have decision nodes. So how are these decision nodes represented? Decision nodes are represented using diamonds. Okay, fine. So now let us see an example. So here we have a decision flag. So if flag is 1, then you have x is equal to a plus b executed. Else you have y is equal to a minus b. So what is the decision node here? Your flag is the decision node. So first let me draw the decision node, which is diamond in shape. Okay, so this is your flag. So if your flag is 1, what operation happens? A plus B operation happens. So what is the process here? Addition is the process. So I put addition. What is the input? The input is A, another input is B. So what is my output? My output is X. Okay. So if flag is 1, I get the output as X is equal to A plus B. Okay. If the flag is 0, what happens? What is the process? The process is subtraction. Okay. The process is subtraction. What is the input again? The input again is A and B. Okay. What is the output? The output is 1. Okay. So here you can connect this A and you can connect this B because both are the same inputs A and B. The output can be either X or Y, but this both occurs at the output. Okay, this you call it as the control data flow graph. It is control actions together with the data flow graph. So where is this control data flow graph used? This control data flow graph is used in many real-time applications. Now let us take a simple digital camera. Okay, so what happens in your digital camera? You have your lens, then you have your CCD sensor. Okay, so what happens here? Your analog data is converted to digital data. Yes, fine. Then image processing happens. So what are the various operations that happens in image processing? You have your correction, audio video correction, or your image correction. Okay, then you have your balance adjusting, and many other processing happens here in this image processing. Fine. Then your encoding happens and then you store your data. Fine. This storage part is a decision node here. So what kind of decision is made here? The user decides whether the output is in JPEG format or PNG format or BMP format, and it goes on. So the output storage is a decision node where the user will decide the image captured or the image captured will be in JPEG format or PNG format or BMP format. Okay, so this example is a real-time example of your control data flow graph. Okay, so all these are process nodes, and the last one alone is your decision node. Hope it is very clear. Now let us look into the next type. The third model is the state machine model. The state machine model is called as an event-driven model. So why is it called as an event-driven model? Whenever there is an event, the system starts functioning. The best example is your ABS, your airbag. So what is ABS? ABS is your automatic braking system, and second is your airbag. So what happens whenever there is an accident, your airbag opens. So that accident is an event. So whenever that event occurs, the system starts function. Okay, so we call state machine model as event driven model. Now you can quickly recollect what is a DFG model called as? DFG model is called as yes, it is called as the data driven model. So your DFG is a data driven model and your state machine model is an event driven model. Okay, so we call this model as reactive. Okay, fine. So what are the various applications in which this model is used? It is used in control application, it is used in safety application, it is used in industrial application. Yes. Okay, now let us see how this model works and what are the various function components of this model. Okay, first let us look into the components. The first component is your states. So what is the meaning of state? Your state is the current situation. Okay, I will just tell you what it means, and then when I draw the diagram, you will understand it clearly. Second is your event. Event means your input. Okay, and the actions means the activity that is going to be performed by the state. And the transition is movement from one state to another. Okay, you will understand this clearly when we draw the model. Okay, so for this state machine model, we are going to take the example of seat belt warning system. Okay, so what is a seat belt warning system? You would have seen in many cars. As soon as you put the key and you turn on the key, okay, now we will talk technically. Turning on the key is called as ignition on. So as soon as the ignition is on, what happens? The system waits for a few minutes. Okay, if the seat belt is on, everything is fine. If the seat belt is not fastened, okay, if the seat belt is not fastened, then what happens? You get a beep sound, okay, and that is through an alarm which is present. Okay, so when the seat belt is not on, okay, what happens? You get an alarm sound. The system seems to be very simple. You're turning on the key. If the seat belt is not put, you get a sound. If the seat belt is put, you don't get a sound. Yes, but inside this system, there are a lot of things inside. Okay, so now we will see all that very clearly. Okay, so I am going to draw the FSM model of your seat belt warning system. So what is FSM? FSM is finite state mission. This model is going to have finite states. So we are calling this as finite state mission model. So what is FSM? FSM is finite state mission model. Okay, so I am going to draw the FSM for your seat belt warning system. Okay, so since there are finite states, so let me first consider what are the three states. The three states are alarm off, then your waiting state, and the third state is alarm on. Okay, now let us see how the system works. Initially, your alarm will be off. Okay, this is your first state. So when will this state change from alarm off to waiting? Whenever there is an ignition. So when the ignition is on, the system gets transferred from alarm off to waiting state. Okay, fine. Now, from the waiting state, is there a possibility of again coming to the alarm off? Yes. So immediately after the ignition is on, okay, if the seat belt is put, so if the seat belt is on, what happens? The alarm is off. Otherwise, if you turn on the ignition also, what happens? The system moves from waiting state to alarm off state. Okay, fine. So the first state is alarm off. If you turn on the key, it moves from alarm off to waiting state. Okay. Now let us consider the other possibility. From waiting state, when it will come to alarm off state, if you put the seat belt, then you will not get any sound. So the alarm will be off. Otherwise, if the ignition is off, again, your alarm will be off. Okay. So now in the waiting state, what will happen? In the waiting state, your system will wait for a few seconds. Now let's take the system is waiting for 10 seconds. Okay. So how is it waiting for 10 seconds? This waiting for 10 seconds is done by a timer. I will explain this timer little later. Okay, but as of now, this waiting 10 seconds is done by a timer. Okay, so it will wait for 10 seconds, and after the timer expire, what happens? The system moves from waiting state to alarm on state. So it will wait for 10 seconds. If the seat belt is not put, it will go to the alarm on state. Okay, now your alarm will start ringing. How long will your alarm start ringing? Will it ring continuously? No, your alarm will ring for around 5 seconds, then automatically it will stop. Okay, so when will it go from alarm on to alarm off state? After this timer expire, this alarm time expire, it will go. This is one condition. Next, otherwise, if you put your seat belt, okay, if the seat belt is on, then again it will go to the alarm off state. And the third one is, if your ignition is off, then also it goes to the alarm off state. Okay, so this is the finite state mission model of your seat belt warning system. Okay, I will simply explain it in 2 seconds. You put on the key. As soon as you put on the key, the ignition is on. The system will wait for 10 seconds. Okay, in 10 seconds, if the seat belt is put, it will go to the alarm off state. If the seat belt is not put, even after 10 seconds, your alarm will start ringing. Okay, this alarm will ring for 5 seconds. Again, this is built using a timer. Fine. Then your alarm will ring for 5 seconds, and after which your alarm will be off. Okay, fine. Now, I told you this 10 seconds and 5 seconds is built using a timer. I will explain how this timer works. Okay, so I am going to draw the FSM model of your timer. So what is FSM? Come on, recollect. FSM means finite state mission. Okay, so what are the finite states here? 3 finite states it has. First one is idle. Second one is ready. And the third one is running. Okay, so initially your timer will be in idle state. So when it move from idle state to ready state, as soon as you load your timer, it will move from idle state to ready state. Okay, fine. Now your system is ready. Now what happens? Your timer will start working. So now let's take, I'm loading the timer with 10 seconds. So what happens? The timer gets decremented. It becomes 9, it becomes 8. So here what happens is your timer is started. Okay, so started means your timer starts decrementing. Fine. Now it is in the running state. After 10 seconds, what happens? It again goes to the idle state. So when will it go to the idle state? If there is a stop or if there is an interrupt, then it will go to the idle state. Okay, so now here, what are the states? You're idle, you're ready, and you're running are these states. Your system has 3 states. So idle, running, ready are the 3 states. Now, these are the current situation. Now you will understand what is the meaning of state. It is the current situation. Okay, now the second component is your event. So what is your event? Event means the input. So here, loading your timer is the event. Starting the timer is the event here. Stop or interrupt is the event here. So these are the events here. Okay, fine. The third is the action. Action is nothing but the activity. So what is the action here? Here, it is loaded with a new count. Okay, here, what is the action? It is decremented. Fine. Here, what is the action? The action is it is waiting for it to stop. Either you can see the action through a flag or an interrupt. So this is the action. Fine. So you understood what are the states. You understood what are the events. Events means inputs. Action means the activity. The last one is your transition. So what is transition? Transition is nothing but movement from one state to another is the transition. So this is a transition. This is a transition. This is a transition. It is the movement from one state to another. Okay, so this is the best example for your state machine modeling. The next model is the sequential program model. Okay, so what is the meaning of sequential? Sequential means step by step, or you can say as one step at a time. Okay, so this is the conventional procedural programming method which you use to program your normal processes. Okay, so just like how you write your program, you program the sequential program model. Okay, to implement this, we either use FSM. So now tell me, what is FSM? FSM is finite state machine, and we have discussed this previously. Or you can use your flow chart to model this. So in this model now, I'm going to explain flow chart. We are going to take the same seat belt alerting system. Okay, so now let us explain this through a flow chart. You know very well what are the various components of flow chart. So first, if the ignition is on, that is the starting process, then it will wait for 10 seconds. Even after 10 seconds, if the ignition is on, it will check whether the seat belt is on. If the seat belt is on, then we have no issues. If the seat belt is not on, then what happens? Then it goes and waits for 5 seconds. What happens during the 5 seconds? Your alarm starts ringing. Okay, after 5 seconds, again it checks for ignition on and seatbelt on, or the time has expired, then your alarm stops. Okay, so this is the basic seatbelt alerting system. So you know where are the various components of your flow chart. So this is your start and this is your stop. These are your processing elements, okay? And these are your decision-making elements. So you have your start, stop, processing, and decision elements for programming using the flowchart, or for modeling using the flowchart. Okay, now let us go into the next model. The next model is the concurrent or communication process model. Okay, so in sequential model, we had a drawback. The CPU, the drawback of sequential model is the CPU utilization is very less. Okay, so why the CPU utilization is less? Because it is one step at a time, only single task at a time. That is the drawback of your sequential model. Okay, so to overcome that, we are going for the concurrent model. This is also called as the communication process model. So what is done in this concurrent model? In this concurrent model, your task is divided into subtasks. Okay, so your task is divided into subtasks. So what happens? Your CPU is used effectively or efficiently. Fine. So once your task is divided into subtasks, then what you do? You do proper synchronization. Okay, then you have to do proper scheduling. I will explain all this. And you need to have proper communication between the tasks. Okay, so now I will tell you what is synchronization, what is scheduling, and what is communication. Okay, now here again, we are taking the seat belt alerting system. Okay, so here in the system, the first step is you are going to divide the task into subtasks. So these are the various subtasks. So your waiting timer is a subtask. Your ignition key status monitor is a subtask. Seat belt status monitor is a subtask. Alarm control is a subtask, and alarm timer is a subtask. So a task is divided into many subtasks. Okay, next is scheduling. What is scheduling? We must know which task should occur first and which task should occur next. Okay, so we need to prepare a timetable, like just like how we have timetable in the class. First period, after first period, second period, after second period, third period. The scheduling is done. Here also, all the subtasks are scheduled using a process called as scheduling. Okay, after scheduling, it has to be synchronized. So what is synchronization? After completion of the first period, your second period should happen.
So after first period, the second period staff should be ready. So that is called as synchronization. Putting the timetable is called as scheduling, and coordinating it for it to happen is called as synchronization. And the last one is communication. So between the first period and the second period, between the first staff and the second staff, there needs to be communication to handle out if there are some misoptions happening. Okay, that is called as communication. Okay, so in your concurrent model, a task is divided into subtasks. Okay, then after it is divided, first scheduling is done, then synchronization has to be done, and proper communication between the tasks has to be accomplished. Okay, now let us look into it clearly. Okay, so like I told you, the first step is it is divided into subtasks. Now let us see what are the various subtasks. Now here we have ignition key status monitoring task. Okay, so what will this task check? This task will check whether the ignition is on or off. Okay, this task will check whether the ignition is on or off. Okay, next you have your alarm seatbelt. Before that, your wait timer task. Once the ignition is on, your timer, the system has to wait for 10 seconds. So this task will wait for 10 seconds. Okay, now this task is ignition seat belt status monitor. So this task will check whether your seat belt is on or off. Okay, now you have your alarm control task. So what will this alarm control task do? This task will check whether there is ignition, okay, and then if there is a seat belt off, okay, then your alarm will be triggered. The triggering of your alarm will be done by this task. The triggering of your alarm will be done by this task. Okay, so how long will this alarm be? It will beep for 5 seconds. So that is again a subtask. So the beeping of 5 seconds is done by using the alarm timer task. Okay, so now this is a task is divided into various subtasks. Okay, now let us see how this works. So initially what will happen, this task will check whether ignition is on or off. Okay, if the ignition is on, what it will do, the control will go to the ignition seat belt monitoring. So it will check whether the seat belt is on or not. Okay, fine. This task will check whether the seat belt is on or not. Fine. Now, before that, parallelly, it will wait for 10 seconds. So after 10 seconds, the control goes to the alarm control task. Now you get input from here, you get input from here, and you get input from here also. All the tasks are happening concurrently, that is parallelly. Okay, now what happens here? After 10 seconds, it will check whether the ignition is on and the seat belt is off. Okay, if the ignition is on and the seat belt is off, what happens? Your alarm starts ringing. Okay, your alarm starts ringing. So how long will the alarm ring? It will ring for 5 seconds, and that input is got from here. Fine. So now you understand this again is the same seatbelt monitoring system. But what is happening here? A task is divided into subtasks and all the tasks are working concurrently. Okay. Once the ignition is on, immediately parallelly 10 seconds it will wait. During the same time, it will check whether the seat belt is on or not. Okay. Now both the control comes here and this will trigger the alarm and the alarm will ring for 5 seconds is done by here. Okay. So this is called as concurrent model. So what is the advantage? The advantage is your CPU is better utilized. Okay. Your CPU is better utilized. So in sequential model, step-by-step process is done, whereas in your concurrent model, a task is divided into subtasks and concurrently operation happens. Okay, now let us go into the next model, which is the object-oriented model. Okay, so here, when you have a complex software, what happens? It is divided into small pieces and the small pieces are called as objects. Okay, the small pieces are called as objects. Okay, so three important features you have. The first one is the reusability. The second one is the productivity. And the third one is maintainability. Okay, now you need to understand what is object-oriented model. Okay, before that, what is an object? Object is nothing but it is a unique piece of a system. Okay, it's a unique piece of a system. Fine, and this piece has a unique behavior and state, and this piece has a unique behavior and state. Fine, so this is called as object. Okay, so now next I'm going to tell you what is a class. So what is a class? A class is a abstract description of set of objects. Okay, object is a piece of a system. A class is nothing but it is set of objects. Okay, fine. Now you can access this in three methods. The first one is private. Okay, the second one is public, and the third one is protected. Okay, so what is private? The access is within the class. The access is within the class. So what is public? It is inside and outside the class. The access is inside and outside the class. Okay, the third one is protected. Okay, so protected, this provides external access. Okay, protected, this provides external access. But the only thing is your parent class can also access. Your parent class can also access. So if you would have studied OOPS, all these concepts would be very clear to you. Okay, so an object-oriented model, a complex software is divided into small pieces called objects. Three important features you have. Then you must know what is an object and what is a class. An object is a piece of system. A class is a set of objects. Okay, you can access this in three ways. One is private, the second one is public, and the third one is protected. Okay, hope this object-oriented model is clear. And the last model is unified modeling language. We will see this clearly later. Okay, but what is this used for? When it is used for design, it is used for deployment. Okay, above all, it is also used for requirement capturing. Okay, using this model, you can capture the requirement. Okay, then you can design, then you can deploy. All the three things can be done by this unified modeling language, and this is called as UML. We will study this in detail little later. Okay, so hope all the 7 models are very clear to you. If you have any doubts, you can contact me. Thank you.